All right, and we're back with projectile motion, assuming my computer ever loads. Are you going to load? Yes! All right, so here we go. The entire thing about projectile motion is that you have a net velocity, which is a diagonal. And if you have a net velocity and a theta, the angle of inclination, you can use some simple trig to break it into the x and y components. Those equations are shown here. Now, you could also do it the other way around. What if you just knew Vx and Vy? Well, you could use the same trig to figure out Vnet and theta. You would probably also want to use something like a squared plus b squared equals c squared. Makes it a little easier. Also, what if you knew just Vx and theta? All right, well, using that equation, you could go from Vnet and theta to Vnet. Sorry, Vx and theta to Vnet. Once you have Vnet and theta, then you could solve for Vy. So really, if you just have two pieces of information, any two pieces of information, you can find everything else. The very first thing you're going to do in any projectile motion problem is take the initial velocity, realize it is a net velocity, and break it into its x and y components. The rest of the problem you're going to do in two parts, x direction and y direction. And you're going to start always with the y direction. Because y direction projectile motion is just free fall. Here are your free fall equations. They're your kinematic equations. The exact same things that we've been dealing with before. They're not that difficult. Ignore the fact that your projectile is moving forward at all, and only worry about the fact that it's going up and then down again. That's all we care about. So, for instance, here is a trajectory. Something launched at 50 degrees, it goes up, it reaches its maximum height, and then it comes back down again. For a simple trajectory like this, here's some things that are always true. The initial position is going to be 0 meters in the y direction. At that max height, which on this picture here is a green dot, right there-ish, the velocity in the y direction is 0. The net velocity is not 0 there, but we're not talking about net velocity right now. We're only talking about velocity in the y direction. And at the highest point, it's 0. Now the time at its max height, we're going to call that half time. Because if you double the half time, you get the air time. In other words, how much time it takes to go all the way to the end. To get here takes exactly double the amount of time it takes to get here. Another way of saying that, it takes half your time to go up, and it takes half your time to come down again. All right, now, when you're there at the very, very end, when you're at the same height as your launch, that means that your time is the air time, which is double the half time, and your y displacement is 0, because you're ending at the same height that you started at. You've literally not gone anywhere. Now, keep in mind that you did have a maximum height up here, call it 10 meters, whatever, doesn't matter. That would be just your y displacement at halftime, at the middle point. The total displacement in the y direction, when you talk about the entire throw, is going to be 0. Because look, you start here at the ground, and you end here at the ground. Let's move on, shall we? All right, so here's a big zoom in of that picture that I was just showing you. And here's the time at that highest point. Okay, it is 1.17 seconds to get from the ground to this highest point. That highest point is 6.73 meters above the ground, and I have traveled in the x direction 11.29 meters. All right, cool. And at the very, very end, the time is 2.34 seconds, which is double. All right, now look at the range. It's also double. Because in the x direction, I'm not speeding up or slowing down. So I travel half my x direction in the first half, and the second half of my x direction in the second half. Crazy. Also check out that height, it's 0 meters. All right, Now, variations. We're still just talking about y direction here. Here, you're starting not at an initial y of 0. In this case, an initial y of positive 4. This means that you're starting at your maximum height, in this case, because we're launching it at 0 degrees. So you can't use it in that t-half to t-air stuff. Now, if you do this, you could still use t-half to t-air, except t-half to t-air isn't going to give you to here. It's going to give you to here, which isn't particularly helpful. So don't do that. What you would do if you were interested in the maximum height is exactly the same thing. You would say, well, I know my velocity, my final y velocity here is 0. I know my initial y velocity is, whatever it is I got from the trig here. And I know my acceleration in the y direction is negative 10. Just using that, you can solve for your height at this point. All right. And then this point, just keep going with the equations. The equations work. But notice here that your delta y is going to be negative. When you go from all the way to the beginning to all the way to the end, your delta y is going to be negative 4 meters. Because I went from positive 4 meters to 0. All right, so those are the 3 variations that you might deal with in the y direction. In the x direction, none of that matters. It literally doesn't matter, because the x direction is always the same. The acceleration in the x direction is 0, because no gravity is pushing it in the x direction. Gravity is pushing down, so you accelerate down. Unless you got a rocket strapped to you pushing you forward, you're not going to accelerate forward, which means once I do my trig to find my x velocity, it's constant. It never changes. So I can use that equation on top there, where I'm going to say x naught is 0 for simplicity's sake, and my acceleration in the x direction is 0, which really just tells me that the range, how far I go in the x direction, is going to be equal to my velocity in the x direction times the time. So if I want the total range, I'm going to take my velocity in the x direction, which never changes, and multiply it by the total time, or the air time. And that will give me my total range. That'll work for here. I take v naught x, and I multiply it by the time from here to here, and I'll get this displacement in the x direction. It works here. There is no velocity in the y direction to start. There's only velocity in the x direction. So I take that number and I multiply it by the time it takes to hit the ground, the time it takes to fall 4 meters, and I will get how far it goes in that time. And it definitely works here, where if I take the x velocity here and multiply it by the time it takes to get here, I will get the range. Now, the big thing for projectile motion, remember, the only thing that is ever the same when you're doing x direction and y direction is the time. So here's what I would suggest. Whenever you're doing a projectile motion problem, I would literally draw a big line down the middle of your workspace and do y direction on one part and x direction on the other part. And the only thing that should be the same, the only number that should be the same on both sides of that line should be your total time. That is the only thing that will ever be the same. Okay, and theta and v net if you want to get super, crazy on me. All right, that was it. Your second 9-minute lecture of the day. Sorry there was so much today, but I think this is probably worth it. I know that the exploration was confusing. All right, now hop over and do the example problems, and you're done. Good work. Oh, I almost forgot. I have a surprise for you. This is my son, Derek. He slept through the entire lecture. Hopefully you didn't. All right, now get to work.